Hi, I'm Deepthi. I'm a software engineer on the Chrome team, and I work on WebAssembly standards. I really enjoyed the WASM Summit last year, and I'm so excited to have this opportunity to talk to you today. I've titled this talk Through the Looking Glass for a couple of different reasons. The first, that I'd like to take a closer look at all of the things that we're working on in the community and talk about their significance. The second, more whimsical reason is that being a part of the WASM community from the early days, this almost feels to me like a rundown of kind of the adventures in WASM land, so to speak. For the most part, I want this presentation to be future-facing, but just to start with, let's take a quick look at where we are today and how we got here. This is a little and mostly incomplete history of the attempts to have native code on the web. I've abstracted this out to the more significant events and the events that have had major influences on the direction of WebAssembly. So way back in 2008, Native Client was announced. So Native Client is a sandbox for running compiled C and C++ code in the browser. It brings the performance and kind of the low-level control of native code to modern web browsers while keeping the security and portability of the web. In 2010, Pinnacle was announced. Portable Native Client, Pinnacle is Portable Native Client. So Portable Native Client extends this native client technology with architecture independence, letting the developers compile their code once and run any website and on any architecture. Now, the problem with kind of the native client and portable native client approach was that it was very specific to the architecture of Chrome, so it wouldn't really work in other browsers. Somewhere around the same time, Emscripten started as a research project. So Emscripten is an LLVM client-based compiler that compiles C and C++ source code to WebAssembly now, but back then the primary compile target was JavaScript, and then ASM.js primarily for execution in web browsers. So around kind of 2010 to 2013, we saw a lot of games being ported to native client and compiled and also compile to use native client in Chrome, but also compile using Emscripten to run in the browsers. But both of them kind of had their own disadvantages. Like Pinnacle, I mentioned, worked only for Chrome, so it wasn't very portable. With the Emscripten and the ASM.js pipeline, you had to do some very specific things to make it performant, and it was easy to fall off performance cliffs if you weren't careful. From 2013 to 2015, there was more collaboration between the tools teams on both ends, and it kind of had the beginnings of WebAssembly, and WebAssembly was first announced in 2015. We spent a lot of time from 2015 to 2017 iterating on the MVP design. In 2017, the MVP was released, and all the major browsers at that time supported WebAssembly as well. So it was very exciting to see kind of this cross-browser collaboration to have kind of these new and interesting use cases on the web. Looking back, it makes a lot of sense to me that the MVP, or the first release, had roughly the same functionality as ASM.js, but with some added advantages, I think. It has safe and well-defined semantics. So it's designed to take advantage of the underlying capabilities of the hardware, so it can execute at near native speeds. It's not quite all the way there, but as close as we can get with the features that the MVP provides. The code is validated and it executes in a memory-safe sandbox environment, and it's also designed to minimize some of the non-determinism we see in C and C++ in general, but that just doesn't work well with the web. It has a compact binary representation. So when you have a WASM module, the information is represented using a dense binary encoding. So, compared to a textual format like JavaScript or ASM.js, that means faster decoding, faster loading, reduced memory usage, and it's portable in the sense that it doesn't make assumptions about the underlying hardware, about the underlying architecture, and that's not already common in hardware that you would see in daily use. The MVP as a starting point has roughly the same level of functionality and aimed at lower level languages. And future features can continue to add functionality in an incremental way. So you have an MVP that has a broad reach, but you continue to iterate on that and add features to make it more powerful. It works well and integrates with the web platform, and that was one of the original goals. But the binary format actually doesn't make any assumptions about the host environment, so it's designed to work well in non-web embeddings as well. This talk is going to have more of a web focus, but there's a lot of great content about what this means outside the web. Lynn's talk at the last summit too about building a new kind of ecosystem is really interesting if this is something that is of interest to you. And because of all this, the MVP picked up a lot of traction. So we saw large real-world code bases compiling to WASM to run on the web, like Google Earth, AutoCAD, Unity. And the best part of all this was that it was consistent across browsers. So it wasn't, you could see the functionality and performance scale in different browsers. And that at that time, that wasn't very common. So large native applications were just able to reuse their existing code to compile to WASM, and applications saw performance improvements over their current web offerings. The load time improvements were significant. Figma, for example, saw WASM cut their load time by almost 3x. So this all sounds really good, right? We should just kind of pack on and move to the next thing. Not really. I think the web is, while the MVP is really good for what it was designed for, it's limiting in a few ways. So the MVP only has numeric values and single-threaded execution amongst other things. The MVP is actually just a minimum viable product. It's just that there's important features that we know that we want and we know that we need, and these are some of the features that we've also been working on. So some of the other things are basically you don't have support for native exception handling, or just being able to work with host objects. But thinking about this over the years, I feel like we've been talking about WebAssembly's post-MVP future for some time now, but it finally feels like that future is here. And the way I look at it, the MVP was just a starting point. To start off, let's take a quick look at what we call the finished proposals, or the proposals that are already a part of the WebAssembly spec but have been standardized after the MVP. Looking at this list, it looks a little ad hoc, and I don't think it conveys the full impact of what it enables. So there are many different reasons to work on proposals. Some of these introduce, ergonomic improvements, like the sign extension proposal, which introduced sign extension operations, or the JavaScript to begin integration, in which JavaScript begins have support for converting back and, we had support for conversion back and forth between begins and 64-bit integer WASM values. The other proposals like reference types, though, are the building blocks for future proposals that are functionally necessary for WASM, and some do both. So let's talk a little bit more about that. We talked earlier about the WASM MVP only being able to use numeric values, so integer values and floating point values. But the reference type proposal introduces a new class of reference types. It adds a new type, externref, that can be used both as a value type and a table element type, and a funcref that can be used as a value type. So unlike other values in WASM right now, the reference types are observed and their values cannot be, unlike the other values, the reference types are opaque and their values can't be observed. As reference type adds support for these opaque values, this proposal also needs to figure out how to store these references. So we repurpose tables as a general memory for opaque data types, and the proposal also adds basic instructions to manipulate these tables. So it turns out that having opaque references is actually quite useful, and quite a few in-progress proposals build on this. There may be other dependencies that I'm kind of papering over here, for example, the interface between reference types and bulk memory, but I wanted to have something that's that's kind of trying to make the point that I'm trying to make here, and that's not conflating too many things at once. For the exception handling proposal, for example, allowing opaque exception objects to be stored in locals and be dynamically type tested is really useful because that means that they don't have to be stored in linear memory. So it uses externref as that opaque reference type. Using externref types, WASM modules can talk to host references directly, in some cases avoiding really expensive glue code. This is useful for both the web and non-web contexts as references. And as the bit pattern is opaque, passing a host object as an externref doesn't really reveal any information about the host. Interface types depends on the multi-value proposal also, which is also on the finished proposal source. The multi-value proposal introduces multiple return types for functions and instructions. In the MVP, basically the functions and instructions consume multiple operands, but can only produce one result. In a stack machine, these asymmetries are kind of artificial, and these restrictions were imposed to kind of simplify the design and the implementation of the MVP. So the multi-value proposal actually lifts these restrictions. So a function or an instruction can have multiple return values. The reference types proposal also introduces a smoother transition path to garbage collection. We'll talk a little bit more about that later, but I wanted to highlight how solving smaller well-scoped problem benefits kind of these future larger open-ended problems. And exception handling, interface types, garbage collection, these are complex large problems that we're continuing to work on. The threads proposal is another example that benefits from decomposing the larger, more complex problems into smaller, kind of these manageable chunks. So the threads proposal allows multiple WASM instances in separate web workers to share a single WASM memory. As with shared array buffers in JavaScript, what this lets you have is really fast communication between the workers. It also adds low-level building blocks for pthread-style shared memory between threads and atomics and futexes. The bulk memory proposal, kind of introduces the optimization of large memcopy and memmove operations, and the data section improvements that the bulk memory proposal introduces actually make the shared libraries work much better, especially with threads. So to kind of explain what I'm talking about, for the threads proposal to share a module, the module has to be instantiated multiple times. So the instantiation initializes the memory with the contents of the module's data segments. So if the memory is shared between multiple agents, it'll be initialized multiple times. And what this means is it can potentially overwrite stores that occurred in a previous initialization. So kind of conditional segment initialization solves that problem. Talking about the import-export of mutable globals. So without the ability to import and export mutable globals, there's not a good answer to provide thread local values that can be dynamically linked. So in the MVP, mutable globals can't be imported or exported. So if we loosen that restriction, we provide a much nicer solution to thread local values. You can do it kind of without too, but it adds some additional overhead, and it's not particularly convenient. So as an example of an ergonomic change which improves future features, non-trapping float to in conversions is one of these. Where it's not 100% necessary, it's a small change, but it makes a semantic difference. So for when you have non-trapping float to in conversions, what happens is instead of trapping on the positive or negative overflow, operations return the maximum or the minimum integer value. So they don't trap. So it's basically switching from the trapping behavior to saturating behavior. So for the SIMD proposal, this is really nice because it's more hardware-like if the operations don't trap. We're going to talk a little bit more about some of these proposals in detail, but I think the point I'd like to make is that a lot of the work we're doing so far is to set the stage and make sure that the building blocks are all there are all there and working to continue to make progress towards these larger problems that we're trying to solve. So I've been talking about the things that we're working on, but I haven't really articulated on why we're working on the things that we are working on. So I'm going to try to do that in the next few slides. Um, Building on the original goals, while the MVP gets us part of the way towards native performance, there's still quite a bit that we can do to get it close to the performance that we see on native platforms. So adding new features and improving performance opens the door to a whole host of new applications. Um, the MVP limits the type of languages that we can bring to WASM to mostly low-level languages like C++ or Rust. But with reference types and a GC extension, we can look at adding a support for higher level languages. One of the things that's suboptimal right now is that calling web APIs from WASM usually means that you have to go through JavaScript, which hurts the performance and adds extra complexity for the developers. But with XTurnRef, it's possible to do this in a more ergonomic way, but it isn't performant. It isn't necessarily more performant than the optimized glue code. This is still an open problem, and we're working on it. So for performance, nothing makes the case for near-native speeds as well as the combined horsepower of Threads and SIMD together. In some of the benchmarks and demos that we've seen that use both of these together, we've seen performance of up to 70 to 80% of native, and this is really huge compared to what we were seeing before with just the MVP. So as we're wrapping up the SIMD proposal, and browsers have actually had support for Threads for some time now, we're starting to see applications that use them together. And SIMD will be shipping in Chrome 91 and Firefox 89. So I'm excited to see more applications experimenting with this and seeing more adoption, and we're opening the doors to new applications. So I'm going to talk a little bit more about the SIMD proposal. The SIMD proposal actually started off really slow, but it's been exciting to see how much traction it's built up over the last couple of years. Let's back up a little bit and talk about the SIMD proposal. The SIMD proposal introduces vector operations in a way that guarantees portable performance. Some of the goals are that the operations should be well supported across multiple architectures. Performance wins should be positive across multiple relevant architectures, and the chosen set of operations should minimize performance cliffs and non-determinism, if any. When we started, we were really unsure whether whether what we come up with would have any positive impact on the applications, given that the limitations of portable performance are kind of directly at odds with how a lot of native applications use SIMD. So native applications actually how native applications use SIMD is they hand tune performance with inline assembly or intrinsics, and it's kind of oriented towards specific hardware. But the really fun part of this has been that we've seen, even with the portable SIMD specification, we've seen this give positive performance wins across multiple benchmarks. It's been great to watch applications use this and work with us to make a full-featured proposal. A really good example of this is the ML applications. The last year has been challenging for many different reasons, but one of the silver linings for me has been all of the ways we've enabled video conferencing apps to build new features on top of SIMD. This is a really good example of something that wasn't as full-featured as it was before WASM or before the addition of WASM and SIMD. In using Google Meet, for example, the web version of, I'm using Google Meet for an example, but the web version of Zoom also uses SIMD. So the background blur, especially, I feel like it's in use quite a bit. And we saw that was a thing that SIMD enabled. While the ML applications were a happy and necessary surprise, SIMD usage in codecs and compute-intensive libraries like OpenCV, cryptography libraries, we've seen those happen as well. While this is, I think we've come really close. We're seeing better performance numbers, but there's still a lot of performance that we're leaving on the table. So what are we doing about it? I'm going to go back to this diagram to talk about the proposals that are currently in flux. So the Fixed with SIMD proposal is actually at phase 4, and we're kind of wrapping up the work on that. But we have a couple of proposals that come out of it. So we have flexible SIMD, flexible vectors, and relaxed SIMD. And the feature detection proposal is kind of a soft dependency there because there are platforms that it doesn't make to have this many operations on. So with the vector operations specifically, we introduce a whole bunch of new instructions, 128-bit value type. So there are platforms like smaller IoT devices where it just doesn't make sense as a feature. So feature detection is basically would let you pick which features you want on different platforms. So with Relax SIMD, we're making kind of a portability and performance trade-off. The existing SIMD proposal imposes strict requirements that each operation has to function the same way on all modern architectures. But this is not really good for performance because what we see is that these instructions, the hardware that provides the hardware support for these instructions is kind of spotty. So you have to emulate them with additional instructions. So that means more code gen and slower performance. But having the performance means that we also introduce some non-determinism, and we have to figure out how to navigate it. And the thing that RelaxMD, I think, aims to do is to optimize for peak performance on individual architectures. The flexible vectors proposal is another one that's kind of trying to leverage the full force of the underlying hardware. So if I was to specifically talk about Intel and ARM, the newer Intel processors have wider vectors. So they have 256-bit vectors, 512-bit vectors, but so fixed with SIMD, which is limited to 128-bit vectors, doesn't actually fully leverage this. And on ARM, you have SVE, which are scalable vector extensions. So the flexible vectors proposal is trying to kind of figure out what makes sense in this, when we look past 128-bit SIMD. Flexible vectors actually doesn't really need the fixed bit SIMD to be a prerequisite, but it's just something that kind of comes out of it. These two proposals are still pretty early stage. We're just getting started, but I wanted to kind of show you how we're thinking about the future. The WASM MVP is limited to a 32-bit address space, so it only has 4 gigabits of memory. Why not more? Why are we limiting this? So there are actually really good reasons to do so. It's easier to sandbox. Most browsers in practice actually don't let you allocate more memory than that. The pointers are smaller, so they're easier to work with. But for applications that need more memory, there really isn't a good solution right now. The proposal is at phase 3 with an implementation in Chrome and with positive interest from Firefox as well. For many applications, 4 gigabits of memory is actually enough, and using 32-bit memory indices is sufficient. But most of the modern ISAs actually can use 64-bit memory addresses. So the Memory 64 proposal extends these existing instructions that are in the MVP to allow 64-bit indices. So there's actually quite a lot of progress on kind of speccing this as well as implementing it. Kind of talking about this, about the C++ and the low-level features, and something that's kind of on the border of both kind of low-level and expanding to newer languages is exception handling. So exception handling is critical for C++ programs that use them extensively, and it's important for other languages that we want to support as well, like Java. So in a web environment, exception handling can actually be emulated during using JavaScript exceptions handling, which kind of provide the right semantics, but it's really not fast. For C++, for example, your code using C++ exception catching in WASM, it's surprising to developers that throwing calls are indirected through JavaScript. So this This doesn't prevent developers from using the C++ standard library. Their code will kind of function correctly, but it's just slower at times, and as long as it doesn't encounter too many exceptional cases. So, like I said, a lot of like threads, SIMD, Memory 64, a lot of what we were talking about is kind of applicable at the lower level. We're talking about the lower level hardware, and we're talking about lower level languages like C++ or Rust. But to bring high level languages to the web, we need the garbage collection proposal. Uh, Currently, there are a few languages that need garbage collection but have ported to WASM. And how do they do this? Uh, Languages that do this actually don't have other options than to compile the GC to WASM as well, and this comes at a considerable cost. So the cost of this can be seen in binary size and the efficiency of the GC itself. The lack of GC is also why some of the reasons why some languages just haven't compiled to WASM. So the garbage collection proposal adds GC capabilities to WebAssembly. So it doesn't actually kind of add garbage collection. It's more of an extension. So what it's trying to do is integrate with the garbage collector provided by the host environment. And a lot of browser VMs actually have industrial strength garbage collectors that are built into them. So the proposal is actually designed to improve interop with the host, making it easier to call the APIs, and just giving it a more cohesive story to make the memory management that much easier. The garbage collection proposal adds the ability to manipulate data objects containing object references. So when bringing garbage collected languages to the web, the motivation of the proposal is to make sure that the support is efficient. This is another example of kind of this large open-ended design problem. There are also several complex trade-offs when you think about garbage collection. So, it has to be fast, it has to be efficient, but it also has to be type safe. So you have to, that kind of slows performance down a little bit. It has to be language independent, and, it has how many languages do you support? How universal is this garbage collector? And really, like another really complex aspect of this problem is, WASM can now be multi-threaded. So what happens when you have multiple threads? So the design of this is still in flux. A lot of these things that I've been talking about could change or couldn't, but a lot of progress has been made recently. V8 has an experimental prototype. There's experimental work ongoing in the tools as well, and we start to see some performance data that's going to inform the design and how we proceed. So the goal of this presentation for me was to highlight the things that we're working on in the WebAssembly community and talk about why they're important and all of the things that they enable. While it would be really great to have this as quickly as possible, the community group and the people in it try their best to make sure that the designs that they come up with are future-proof. We've kind of the undercurrent through this is that these are hard problems to solve. Concurrency, non-local control flow, garbage collection, working with interfaces, and the things that really keep us honest here is working in an open community group. So while this can be frustrating and sometimes really slow us down, it's a place where different people with different goals can come together and work on a standard. It also provides kind of these checks and balances to make sure that the progress we make is sustainable and the things we design are the building blocks for the future. Another interesting things that I've learned over the years is that the only thing constant is change. This sounds really kind of like a soundbite and cliche, but what I'm trying to say, I think, is that as WebAssembly has continued to evolve, we've seen new cases open up, new developers contribute, the ecosystem changes, and the standard continues to change with it. And amend its goals kind of to be inclusive of all of the changes. So this is a thing that makes me really optimistic about the future, that we evolve with our ecosystem. If you'd like to know more, about the design of these proposals or contribute, and you have ideas, join us in one of our meetings. We have online meetings once in 2 weeks, and we also have, in-person meetings when we're back to having them again. You can join the community group file issues on the design repo as well. So thank you for listening.